Ya, ahora sí. Okay. Está.
Vamos a esperar un par de minutos a que llegue más gente.
No hay gente.
¿Los llamamos desde aquí? Oye, deberíamos de poner bocinas en todas las oficinas para que los que no vengan al coloquio puedan nada más escucharlo, ¿no? Sí. Podríamos ponerlo para transmitir, como que sea radio IA.
Radio ya.
Sí, radio IA. Ajá. Radio IA. Pues bueno, creo que podemos comenzar el coloquio del día de hoy. El día de hoy es un placer tener a Joel Sánchez Bermúdez de la ESA en Chile. Mi introducción va a ser muy breve porque Joel tuvo la amabilidad de preparar un slide precisamente con su introducción sobre su background académico. Y pues en general Joel trabaja en estrellas masivas, en estrellas O y Wolf Array. Y el día de hoy nos va a platicar sobre Gravity VLTI Chromatic Image Reconstruction of Eta Car Win-Win Collision Region. Así que, por favor.
Bueno, hola, muy buenos días a todos. Yo soy Joel Sánchez. Actualmente soy postdoctoral fellow at the European Southern Observatory, based in Santiago de Chile. And my main areas of research are the study of the physics of massive stars, in particularly O and Wolf-rayet stars, with high angular resolution techniques. I'm specialized in the use of infrared interferometry, and particularly in image reconstruction for infrared interferometry. And today I will talk about a project that I have been developing during the last 2 years, which has as a goal to study with milliarc-second resolution the core of one of the most astonishing objects in the sky, which is Eta Carina. I'm quite sure all of you have heard about this source, which is a very massive star surrounded by this bipolar structure known as the Homunculus Nebula. And so here on the screen, you have the light curve. I have a pointer. You have the light curve in the V band for the last 2 centuries. And the idea is basically that the homunculus was created during the 19th century in what is called the Great Eruption, which was a violent episode of mass ejecta that lasted for around 20 years. And during that time, the star or the stars at the core of Eta Car released between 12 and 15 solar masses at an average massless rate of 0.6 solar masses per year, with, let's say, terminal velocities of the winds of around 650 kilometers per second. After that, Eta Carina faded, right? And then it stayed there more or less stable until the end of the 19th century, where there was another small eruption that lasted 7 years. And then it only released 0.1 solar masses with a terminal velocity of 300 kilometers per second. This secondary eruption actually created something that is called the little homunculus, which is embedded into the big blobs of the Homunculus Nebula that we normally see in the Eta Carina images. And after that, the system remained more or less stable until the 40s in the 20th century, where the luminosity started to rise up again. And then it has been rising continuously up to now. But what is interesting here is that during the 90s, Lamitelli and collaborators observed a correlation between the variability in the H-band, in the light curve in H-band, with the effective width of the helium-1 lines at 1.08 microns. And they found that there was a repeatability in the signal that lasted for around 5.54 years. And then those authors suggested that the repeatability in this in the signal here was actually created because of the presence of a secondary source in the core of Eta Car. So the idea was that Eta Carina was not a single massive star, but a binary system. Sorry, well, so the idea is that they use the light curves in the near infrared, in the visible, and also in X-rays to derive some of the physical parameters of the system. So what we know so far is that the central star is a very massive star, probably a luminous blue variable with a mass of more than 100 solar masses, close to the Eddington limit, with an estimated mass loss rate that oscillates between 10 to the minus 3 to 10 to the minus 4 solar masses per year, with a very dense and dense wind that travels at a terminal speed of 400 kilometers per second. The parameters of the secondary are less constrained, basically because nobody has seen it directly, right? Nobody has been able to resolve the secondary source in the core of Eta Car. And we only know because of their existence because of the changes of variability in the light curves, changes in the helium-1 lines, and also because of some ionization effects in the central R-second at the core of Eta Carina. But the idea is that we have a secondary source that is a hot star, probably a no-3 star, with a mass loss rate of around 10 to the minus 5 solar masses per year, with a much lighter wind but faster one that travels at a terminal speed of around 3,000 kilometers per second. And here I plotted the projected orbital solution derived by Teodoro and collaborators in 2016. And this is more or less how the orbit looks like projected in the plane of the sky. And here I put some of the orbital parameters, and from here you can immediately see that the orbital solution is actually quite eccentric. No? 0.1 is the estimated solution. But again, those parameters are not fully constrained, right? Because those values have been only derived by indirect measurements. So as I said before, nobody has been able to observe the secondary source in Eta Carina. And here I plotted the homunculus nebula with some of the position angles in this part projected in the plane of the sky, and in this part projected in a plane formed by the sky plane and the line of sight of the observer. And I want you to notice two things here. First is that the orbital solution derived by Teodoro is actually perpendicular to the semi-major axis of the homunculus nebula. And second is that with this orbital solution, the secondary remains in front of the primary for most of the orbital passage, right? It only goes behind the primary when it approaches and passes the periastron. And this is interesting because if this is true, then we should be able to observe all the effects of the secondary, of the effects of the wind-wind collision zone between the two stars for most of the orbital path for the 5.5 years that last the period. Up to now, there has been only 2 attempts to image with milliarc-second resolution the core of Eta Carina. So here you have in N band the central 3 arc-seconds. This is an image obtained with Visier at the VLT. And then here you have 2 reconstructed images. These images here were obtained with infrared interferometric observations. The first of them, the one at the top, was obtained with AMBER. So AMBER was an instrument located at the VLTI that allowed the simultaneous combination of 3 telescopes in order to perform interferometric observations. So this image was actually reported by Weigel and collaborators in 2016. We observed that the core, the central 20 milliarc seconds, is actually asymmetric. They call this shape a fan-like shape morphology for the object. And well, this image was particularly reconstructed in the blue shifted part of the bracket gamma line in the K-band. The second one was obtained with Pioneer. Pioneer is also another instrument of the VLTI that allows the combination of up to 4 telescopes, and it works in the H-band, 1.7 micrometers. And the idea here, but the difference is that Pioneer only allows us to reconstruct images in the continuum. So the image that we observe here is actually a continuum image of the core of Eta Carina. This elongated and compact core is in fact identified as the primary wind of Eta Carina. So 2 things to recognize here is that it is elongated, and the position angle of the elongation is actually consistent with the position angle of the homunculus nebula. And second is that it has an average size of 2.3 milliarc seconds, more or less. So we had this information in hand, and we say, okay, then we go again to the VLTI, and we try to observe again the core of Eta Carina to see if we can get more insights of how is it, and try to obtain more information about the physical parameters of the interaction of the two stars. So for those of you who don't recognize the VLTI is basically this complex. It's located in Cerro Paranal at the northern part of Chile. And is composed either, well, the interferometer is actually composed either with 4 8-meter telescopes, the 4 unit telescopes, or 4 2-meter telescopes. The 2-meter telescopes are actually movable stations that allow us to reconfigure our baselines. So the maximum baseline that we could get is around 130 meters, which allow us to obtain an angular resolution of more or less 2 milliarcseconds at 2.2 microns. So at the distance of Eta Carina, this is equivalent to observe at the resolution of 5 AUs, more or less 2.6 AUs. Sorry, 4.6 AUs. And since the last 2 years, we have a new, and I think it's a very fantastic machine called Gravity, which is this instrument here, which is the new beam combiner at the VLTI. So it works in the K-band, in this regime, from 1.9 to 2.5 microns. It allows us to obtain this angular resolution, but it also allows us to obtain for the first time in the near-infrared phase reference visibilities to perform narrow angle astrometry with a precision of 10 microarcseconds, dual field observations of 2 simultaneous sources in the sky at the same time. It comes with 3 different spectral resolutions, 50, 500, and 4000. So for the high spectral resolution mode, it also allows us to resolve some of the broader lines in the K-band spectrum. And the limiting magnitude is 16 in the K-band. And I just listed here 3 technological developments which I think are quite interesting for this machine. So the first one is a new infrared waveform sensor called the Chiao units. The second one is the star separator, which allows us to perform the dual field observations. And the third one is that the beam combiner, the device that allows us to perform the interference of the line, it's nothing else than an integrated circuit. And that is quite amazing for this machine.
This is fed with the 4 big telescopes?
Yes, you can work either with the 4 big telescopes or with the 4 small ones. You can well, you only gain in sensitivity with the big ones. No? In resolution is the same because you have 130 meter baseline. Exactly. So I just want to highlight some differences between infrared and radio interferometry. So normally in radio you work with the amplitude of the visibilities and the Fourier phases or the phases of the visibilities, right? But in optical or in infrared we have to use the square visibilities, right? So the mean power encoded in the fringes, and we use something called the closure phases. We use the closure phases simply because the atmosphere induced telescope-dependent errors above each one of our stations. So when we obtain a phase measurement, this phase measurement is actually affected by these atmospheric terms. So in order to eliminate these atmospheric terms and only obtain a phase measurement that depends only on the brightness distribution of the source, we perform a triple product of visibilities. And those visibilities, or the triple product is formed by a closed triangle of, it's formed by the visibilities that are obtained by a closed triangle of baselines. So in this way, we end up with a phase information that is only that depends only on the brightness distribution of our target, right? And is not affected by the atmosphere. But it's important then to remember that then we don't have a one-to-one correspondence between the amplitude of the visibilities and the phase information. So we cannot perform a simple Fourier inversion like in radio. And we cannot use clean to reconstruct our images. And then the image reconstruction becomes a more complicated problem here. So, but going back to Eta Carina, so this is the UV coverage that we got with our first observations during the commissioning phase of the instrument in February 2016. So very homogeneous UV coverage, only obtained during 2 nights of observations, 14 data sets. And just for comparison, I put here the UV coverage obtained with the previous AMBER observations reported by Weigel and collaborators in 2016. So again, a very uniform UV coverage, but they have to use 56 data sets. And they obtained all these data sets between December 2013 and March 2014. The difference is that with the previous beam combiner at the VLTI, you can only combine 3 telescopes. So you only have 3 baselines and one phase measurement per snapshot, right? And now with Gravity, we can combine 4 telescopes, so we have 6 baselines and at least 3 phase measurements per snapshot. So it's much more efficient to do images now here with Gravity. I just put here the maximum angular resolution obtained with Gravity, 1.75 milliarcseconds, and with AMBER 3 milliarcseconds. And this is the setup that we use for our observations. So this is what we got with gravity. So this is the normalized and calibrated Eta Carina spectrum in the K-band. So you can immediately identify several lines. The two most prominent ones are bracket gamma here and this helium-1 line here, which actually has a P Cygni profile. So it's the helium-1 to S2P line there. And just as an example, I plotted here versus wavelength the differential visibilities and the differential phases. And you could immediately notice that there is a difference in the morphology at the position of the line compared to the continuum channels, no? And actually, at the position of the lines, the structure appears to be more resolved. And since we have non-zero phases here, sorry because of the resolution, but the idea is that the structure here is actually quite asymmetric. No? And the idea is now to use this information to try to recover the images. But with gravity, we not only get the interferometric data at the desired spectral resolution, so in this case 4000. We also get continuum data from the fringe tracker. And these are the square visibilities at two different position angles. And the idea here is that we perform a geometrical model fitting of two different Gaussians just to estimate the sizes of the continuum of the Eta Car continuum. And then we compare this with previous estimates from other works. For example, with Van Burkel 2003, Weigel 2007, 2016. And we derive a similar elongated ratio at the same position angles that with previous estimates, but a little bit more, with a little bit more precise measurement with gravity. And this also helps us to calibrate our instrument. Remember that these were some of the first observations obtained with gravity, so we needed something to compare with in order to properly calibrate the observables that we were getting. So as I already showed you the spectrum, so we have the spectrum in the K-band, so we say, okay, why not model the spectrum? Why not try to reproduce the lines that we observe here in order to obtain some hints about the physical properties of the primary star, and then compare this with previous works. And this is something that we did, sorry?
So the source is resolved. Is this the combined spectrum or is this the spectrum in the center?
No, this is the total spectrum. So this is the spectrum that you got per telescope, let's say. But actually, you have the spectrum, you also resolve, yeah. That's more tricky, but yes, you also have that. So this is, again, the total spectrum. You have here in blue the measurements obtained with gravity, and then you have two additional lines. One, the red one, is our best fit model. And then you have a black one, which is a reference spectrum that we use from previous work of Gruet and collaborators in 2012, which in fact was based on previous models obtained by Hillier in 2001, 2004, and so on. And the interesting thing here is that previous estimates or the previous parameter of the group model could not reproduce the helium-1 lines observed in the gravity spectrum. So if you see here, the black line is actually not following the trend of the helium line here and also here, right? Which is something that we could reproduce with our new model. And the difference between the two models are actually the effective temperature of the central source and the difference or a factor of 2 in the mass loss rate. And this is not something unexpected. In fact, there has been a large debate in the literature over the last 20 years about changes in the mass loss rate of Eta Carina between a factor of 2 and a factor of 4. The problem is that these kind of models are not, cannot be conclusive, and cannot be conclusive because it can only, CFMG only allow us to introduce 1D symmetrical models, and then for only one source. And then we have already seen from the visibilities a couple of slides ago that we have something that is resolved, that probably we have a secondary source and that is asymmetric. So this is a good starting point, but we need to be careful with this kind of models because there are more, the core of Eta Car appears to be a more dynamic environment, right? And then, so if this was true, and then these lines were only created by the primary star, then, for example, the helium-1 line should be formed at the very near or very close to the central source, less than 2 milliarcseconds, which is this red line here. While bracket gamma could be formed perhaps at a distance of 5 milliarcseconds or so. But let's see if this is if this is consistent with what we see in our interferometric images, now that we could finally resolve the emission in the core of Eta Carina. So, as I say, imaging for near-infrared interferometry is something more complicated, we cannot use the simple Fourier inversion. So in fact, imaging is a regularized minimization process. And basically, to minimize this expression here, and we have two terms. The first term is the likelihood. So it's basically the difference between our interferometric, minimize the difference between our interferometric observables and the observables that are produced with the model image that we are trying to recover, plus a regularization term. And this regularization term actually encoded some a priori information that we have about the brightness distribution of the source. And here we can introduce, there are many regularization functions that we could use. The L0 norm, the L2 norm, we can use entropy, total variation, and so on. And there are several softwares in the community that we could use in order to perform this minimization. Some of them are based on Monte Carlo methods, like for example, squeeze. Some others are based on gradient descent methods like DSM, Myra, Painter, and so on. And this is exactly what we did. So we use a squeeze. So it's this software developed by Fabian Baron in 2010. And we image first bracket gamma in this regime. So these are just the parameters that we use for our reconstruction. And I just wanted to point it here that we use 3 different observables to simultaneously recover a cube of images across the bracket gamma line. So we use the amplitude, so square visibilities. We use the closure phases, but we also use the chromatic differential phases, the wavelength-dependent differential phases that actually monitor the flux centroid displacement across the line. Right? And then we use 3 different regularization functions. We use the L0 norm to avoid the spurious point line sources in the pixel grid that we're using. We use a Laplacian because we know that the source is extended. And we also use a transspectral regularization to ensure some spectral continuity between the different channels that we were trying to recover. And here you have again the spectrum. And now I finally showed you the reconstructed images. So I know that if you normally do radio interferometry, probably you say, well, this is super trivial, but believe me, for the infrared, this is top notch for the moment. So the idea is that in the continuum we have this very compact core, this elongated core, right? And as we move towards the line, we observe how the structure is extended and asymmetric towards the southern part. No, this is just the line. This is just across the line here.
You don't really get the continuum.
Well, just these channels here at the edges. When I say the continuum, I'm referring to the channels here. But yes. Sorry, I had an HDMI, but it couldn't be used. So sorry for that. It's high resolution technically. Yes, exactly. Well, the idea is that you observe this asymmetric structure here, and in the blue shifted part, you can see a kind of arc-like an arc-like shape here at some point, probably like a kind of front shock here, right? And just to show you how, so I show here, for example, the square visibilities versus spatial frequencies, and here the closure phases versus spatial frequencies. In gray are the data points, and in blue the best fit image that we could recover. And I wanted to show you this just for you to check that we actually recovered quite well the observables. For some channels it was quite difficult because they were very, very noisy because the correlated flux was very, very low also. But in general, the images follow the trend of the 2 observables there, and it was the same case for the differential quantities. So you have here versus wavelength the differential phases per baseline, and you have versus wavelength the differential visibilities per baseline. In blue are the data, in green are the observables obtained from the images, and we could fairly reproduce most of them for all the different baselines with our reconstruction. And then we obtained a second data set with gravity, obtained in May and June 2010, 10 different data sets. This is the UV coverage that we got, but unfortunately here, the UV coverage was not so good to be able to recover a high fidelity image, or at least an image, right? But at least with this second epoch, we were able to compare some coincidental baselines between the 2 data sets that were similar in both of them, right? So I have here a comparison of 3 different baselines, and a small one, an intermediate one, and a large one. And as you could clearly see, so in blue you have the 2016 data. In in purple you have the 2017 data, and as you can clearly see, there are already some difference in the observables obtained between the two different epochs. And this is what this is indicating us is that there is a time-dependent evolution of the morphology. Unfortunately, we don't have a second epoch of images yet, but at least we have some hints that the environment is actually quite dynamic and is changing in a period of perhaps a few months only, right? So how do we interpret this? How do we interpret what we see in the images? What is the model? What can we learn from there? So there are some hydrodynamical simulations already developed by Thomas Madura in these two papers, 2012 and 2013. And this is basically the idea. So we have a very massive star with a very dense wind in the core. And then the wind is moving at 400 kilometers per second. And we have the secondary source. And the secondary source has a much faster wind, 3,000 kilometers per second. When the secondary moves around the primary, it opens this cavity around it. So it distorted the primary wind and opens this cavity here. And we suspect that because of the orientation of the system in the plane of the sky, what we are observing is actually the material coming or flowing along the cavity walls opened by the secondary in its orbital motion around the central star. So this is more or less how we interpret the diagram. So we have a pre-shock primary wind here. So this is the central star. The primary, we have here the secondary, as we would see it in the plane of the sky. Then we have the interaction zone, the wind-wind collision zone here, which opens this conical cavity. And then we have this pre-shock secondary wind. And then flowing along the walls of the cavity, we have this post-shock secondary wind. But because of the orientation in which we are observing the system, we are preferentially oriented toward the southern wall of the cavity here. And then this is exactly what we are observing in the reconstructed images. Or we suspect that that's what we are observing in the reconstructed images. So this is again at an orbital phase of 0.5. We have the conical cavity opening. This is projected in the orbital plane. So we have the conical cavity opening, and then as the secondary moves, this cavity is actually distorted, so it becomes a kind of spiral. And at some point, the leading arm of the cavity actually collides with the trailing arm of the previous periastron passage. And then they form this compressed shelf of primary winds here. And then what we are observing, for example, with the gravity images, is actually the inner, or the most inner compressed shelf of primary wind at the core of the system. And we suspect that this R-like shaped thing here that we observe is actually the material flowing around the most recent compressed shelf of primary wind form in the previous periastron passage. How does this compare with the amber image, in which we observe a more extended structure? And the idea is that, well, basically this is expanding. The Madura model suggests that it is expanding at more than 400 kilometers per second. And then what we observe here in this orbital phase, which is actually later in the orbital path, closer to the next periastron passage, is the disruption of this. Well, it's basically this compressed shell that is disrupted and clumped, and then it has the form. And the two antennas that Weigel identified, one here and one here, are just parts or portions of this compressed wind, of compressed primary wind over there. We have just qualitatively interpreted our results with this model. We still don't have proper simulations to put some numbers in there, but this is something which we are working now on. But with gravity, we not only get images of bracket gamma as with amber. We also managed to get, for the first time, images of the helium-1 line. And here you have, again, the setup that we use is quite similar to the ones that we use for the bracket gamma line, now this time in helium. And we've managed to recover also images in this line here. And here you have, again, the morphology that we obtained. And this is actually quite interesting because as you remember, the first works in which the hypothesis of the second or the binary at the core of Eta Carinae was formed were actually based on the variability of the helium-1 lines in the near infrared. But nobody has been able to constrain or to put some numbers about the sizes of the line emitting region up to now. Now these are the first images at this resolution in which we resolve the line emitting region. It's as simple as that for the helium-1 lines. And here you have again how it fits the interferometric observables. And this is more or less how do we interpret what we see in the line. So we use the models developed by Clementel in 2015, these two papers here. And we basically have the same morphology. So the primary star here, the secondary here, the cavity walls here. And then we have different regions composed by different by helium in different ionization states, right? We have here helium 0+. Then in violet here or purple, we have helium+, which is actually the one responsible for the helium-1 lines. And then we have totally ionized helium 2+ in these green regions here. And we suspect that what we observe in the images are coming mainly from region 3, region 4, and region 5. Region 6, according to these models, is 3 orders of magnitude less dense than the other 3 regions. So we suspect that this does not produce a lot of, it's not responsible for the emission that we are observing in the line. So but it's interesting to notice that the sizes of these different regions depends on the massless rate. So for different massless rates, we have different line emitting regions. So for example, for a massless rate that is close to 10 to the minus 4 solar masses per year, we should have a very extended region for the helium plus. So the images should be quite extended, and actually we should not be able to see these differences as we move in the line profile, no? Because it's basically all the emission is coming from all the directions here, no? But this is something that we are not observing. We suspect that we are observing something between these two values of massless rate here, between something about 10 to the minus 3 solar masses per year to 0.5 10 to the minus 4 solar masses per year, right? Because of the extension of the line of the emission that we are observing in the reconstructed images. So this is more or less what we suspect. So we suspect that, for example, at the value of the line, regions 3, 4, and 5 are actually the ones that contributes more to the morphology here. Then, as we move towards this inflection point, let's say, region 3 and 4 contributes more. And then at the peak of the line, regions 3 and 5 are the ones that are contributing more to the observed morphology. Again, up to now we have been only to reconstruct the images and to qualitatively analyze them with previous models in the literature. But the interesting thing now is actually to model these lines, particularly for these observations, and see if they are consistent to what we suspect that we are observing. And just to summarize, so we found the continuum elongated core is consistent with previous near-infrared interferometric observations, also obtained with the VLTI. We observe an extended structure in the images that are consistent with a wing-wing collision zone scenario. The most extended emission is observed at blue shifted velocities, so the material coming toward us, which is also consistent with the fact that the secondary is in front of the primary at the orbital phases in which we are observing it. There is a time-dependent changes in the observables at all the spatial scales. We conclude this from the comparison between 2 different gravity epochs. We managed to obtain the first reconstructed images at milliarcsecond resolution of the morphology of this helium-1 line. And then, as I said before, future radiative transfer and hydrodynamic simulations will allow us to constrain the physical parameters of Eta Carinae. And finally, say if Eta Carinae will die as a supernova or not, no? Because that's the main question so far. And that's all from my side. Thank you very much.
Questions? Comments? Chicho?
¿En español? Hay algo que no entendí muy bien. Si entendí la órbita tiene un tamaño como de 10 milliarcseconds.
Sí.
Tú tienes píxeles de 0.6 y una resolución de menor de 2.
Ujú.
Entonces dices que no notas, nadie ha detectado la compañera.
No.
Cuando yo vi las imágenes, en efecto, nunca hay 2 puntos, ni mucho menos. Y según tus modelos, no es que estés viendo a las estrellas, sino estás viendo el viento.
Sí.
Pero como son 2 vientos, yo esperaría que tus imágenes se movieran, digamos, de una a la otra estrella. Y me parece que los modelos, además, están centrados en el viento de la secundaria. Entonces, ¿no es equivalente eso a ver la secundaria?
No, bueno, realmente nosotros creemos que vemos el viento de la primaria, que de hecho es muy denso y de hecho es ópticamente grueso. Entonces nosotros vemos esta emisión, por ejemplo, en bracket gamma, simplemente porque se abre la cavidad y la cavidad nos permite ver a través. De otra manera no lo veríamos. La secundaria, de acuerdo con las estimaciones de Weigel, la idea es que es 100 veces más débil que la primaria y no tenemos la sensitividad suficiente para poder observarla. De hecho, está embebida en el viento de la primaria y no la podemos ver. Entonces, lo único que vemos es este material fluyendo a lo largo de la cavidad y sospechamos que es esta cavidad en la parte sur, ¿no? Por la orientación de la órbita que tenemos, ¿no? Que es más o menos como interpretamos el modelo. Pero la secundaria, desafortunadamente no pudimos, la idea era resolverla realmente, pero no lo podemos ver. Sí, la resuelves, pero no la ves. Y bueno, estas observaciones se hicieron con los ATES, con los telescopios pequeños. La idea era observarla de nuevo con los UTES para ver si con más sensitividad podíamos obtener algún hint de la secundaria, particularmente ahora que está cerca del apastron.
Margarita.
Sí, me parece muy interesante tu trabajo y me surgen pues muchas interrogantes. Todo esto dependería entonces del ciclo, de cómo vaya pasando la secundaria, como de cuánto sería.
El periodo es 5.5 años.
O sea, bueno, hay que ver, ¿no? O sea, sería interesante ver. Pero si hablas de choque de vientos, también en rayos X se debería de ver algo.
Sí, se ve.
Así.
Por alguna razón se saltó la diapositiva.
No venías preparado, pero.
No venía preparado, pero. Ahí está. Ah. Oh. No sé dónde se fue. No se ve. Ah, pues es justo esta, mira. En rayos X, con el Rossi X-Ray Timing Explorer Satellite.
¿Cuál es?
Esta es la curva de luz, entre 2 y 10 kiloelectronvolts. Y ves esta periodicidad. Esta periodicidad dura 5.5 años. De hecho, los parámetros de la secundaria, la tasa de pérdida de masa y la temperatura efectiva y la velocidad del viento se derivan a partir de la curva de luz en rayos X. Porque es la única manera que tenemos de estimar la tasa de ionización
Y la otra cuestión, una última es, bueno, ya que estás en el infrarrojo y todo, en la de 2.12 no ven hidrógeno molecular.
No se alcanza a ver. No.
Nada más. Gracias. Me voy a pasar aquí.
No entendí bien la estimación de la masa de la secundaria. ¿Podrías explicarnos un poquito más?
¿De la masa de la secundaria?
Sí, no mostraste un cálculo de las...
Sé que este paper de Pitard y Corcoran del 2002, que usan las observaciones en rayos X para estimar los parámetros de la secundaria. Pero se piensa que es una estrella caliente, como digo, una O3, y que la masa es alrededor de 30 masas solares. Pero como les digo, los parámetros son todavía inciertos porque no se pueden constreñir muy bien aún. Entonces, la idea es ahora utilizar estas observaciones en las que espacialmente resolvemos o queremos resolver el choque de los vientos y a partir de ahí con con el monitoreo en diferentes fases orbitales, modelar y ver si son consistentes con las estimaciones previas de los parámetros físicos de las dos estrellas.
¿Sí sería de cualquier manera una estrella masiva?
Sí, sería una estrella masiva. Se piensa que es una Luminous Blue Variable de más de 100 masas solares. De hecho, se cree que está cerca del límite de Eddington y no se sabe exactamente si es estable o no estable. Es uno de los problemas principales que existen, es si el viento de la secundaria, cuando pasa cerca del periastrón, es capaz de llegar a la superficie de la primaria y extraer material de ahí. Y si esto, de hecho, puede acelerar o frenar los periodos episódicos de pérdida de masa, o si esto puede acelerar o frenar la explosión como supernova de todo el sistema. Esa es una de las interrogantes que aún existen. Sabemos, por ejemplo, que las líneas de helio varían un montón en fases muy, muy cercanas al periastrón. Los cambios son del orden de días. Entonces, la idea sería hacer imágenes o tratar de hacer imágenes de la morfología cerca del periastrón con unas pocas semanas de diferencia y ver cómo cambian y ver si los modelos son capaces de ajustarse a esto o no. Porque la pregunta principal es si Eta Car va a explotar como supernova o no va a explotar como supernova. ¿Y cuál es el efecto de la secundaria sobre la primaria? ¿No? Es la tasa...
Rafa.
Sí, bueno, ese era precisamente...
Bueno, la idea es que, por ejemplo, si la secundaria es capaz de remover momento angular de la primaria y masa, o inhibir la tasa de pérdida de masa de la primaria, inhibir la explosión, pero tampoco se sabe.
Aquí Rafa tiene una pregunta.
Si las señoras me dejan hacer la pregunta, en realidad mi pregunta estaba exactamente dirigida a eso. Eso es un sistema que da la impresión que dinámicamente es muy inestable.
Sí.
Entonces, tiene que ser muy joven. ¿Alguien ha hecho algún modelo de qué tan joven puede ser este sistema? Simplemente por decaimiento de la órbita. Tiene que ser un desastre.
No tengo estimaciones de eso.
Nadie lo ha hecho, que tú sepas.
Sé que es joven, tener un par de millones de años, pero...
Okay.
O sea, más que eso no te sé decir. Es 100 masas solares, 1 millón de años de edad o algo así.
Bueno, pero si fuera muy inestable, estaríamos viendo un cambio en el periodo sustancial, ¿no?
Sí, hay cambios.
¿De qué orden?
En los últimos pasos del periastrón hay pequeños shifts del orden de días, 15 días o 20 días, comparados con las estimaciones del periastrón pasado, ¿no? de los periastrón que le preceden. Sí hay pequeños cambios. Y de hecho, es lo que mucha gente dice, bueno, estos pequeños cambios de hecho sugieren un cambio en la tasa de pérdida de masa. Y hay un montón de papers que hablan de cambios en la tasa de pérdida de masa entre 2 y 4, un factor de 2 y 4 en los últimos 20 años. El problema es que la información no es totalmente completa en todas estas estimaciones, porque unos no incluyen los efectos de la secundaria, otros no incluyen los efectos de la cavidad, ¿no? Y cómo se distorsiona a lo largo de la órbita, y si el ángulo de visión es preferencial hacia nosotros o no, etc. Entonces es un sistema muy, muy complejo como para dar una estimación concreta de estos parámetros. Eso es más o menos lo que sabemos. No lo sé, no lo sé.
Bueno, vamos a darle las gracias de nuevo y tenemos el after party para que sigamos discutiendo.
Gracias.